Hello everyone, this video is part one of analysis of variance, which we call ANOVA. This is an incredibly powerful test. It is one of the favorites. It can get really complex and there's a lot of different kind of subcategories of ANOVA, but it is very flexible so we can do a lot of things with it. This is how we tell the difference between multiple groups. With the t-test we have two groups, now we can actually do three or more different groups. Our hypotheses. The null hypothesis, just like all the other null hypotheses, runs under the assumptions that everything's equal. So there's no difference between any of the groups. The alternative hypothesis is that there is a difference between all of the groups. So not all of these means are equal. Group 1, 2, 3 are equal is the null. Groups 1, 2, and 3 are not equal is the alternative. You can also do a research hypothesis that is any combination of the means are not equal. So you can say A and B are equal, but not equal to C. If you decide to do that, you better have a really strong rationale and a good literature base or pilot to support that. Typically, we just say all equal or not equal. This is number one in popularity. In fact, some stats people never use a t-test because they know if it can do it. It's a little bit more powerful. And it was invented by Fisher. So just think about what it takes to invent a statistic. He is brilliant. Born in England in the 1900s. He wrote a bunch of manuscripts. He got into big fights with Pearson, who is the guy that does all the correlation stuff. His work was strongly influenced by this guy who published under the name Student because he worked for Guinness and couldn't publish under his own name. It's really what it comes down to. Student's T is the main t-test that we use, so he just expanded on that. He was a professor at Cambridge. After his son was killed, he didn't publish as much, which was really sad. He also was a consultant for the tobacco company and was really big on the connection and effect and relationship between smoking and lung cancer. He said that we can't make that claim, we don't have enough evidence, and sadly died of a different kind of cancer in 1962. If you would like to read his biography, it's called Fisher, The Life of a Scientist, for some light reading. He looks like a stats person, doesn't he? All right, ANOVA. We have three major assumptions. First of all is normality. So if I'm looking at three groups on their stat scores, I need to make sure that each group is normally distributed. So I'm not just looking at the combined variable, I'm looking at the variable broken down by groups, and each group needs to be normally distributed. Homogeneity of variance is another really big assumption. So again, we want all three groups to be pretty much varied in the same way. We don't want group A to be clustered around the mean and group B and C to be spread really far around the mean. We want them to be pretty much the same. And then independence of observation. So what that is saying is that each score is its own score, meaning I'm not working with groups, my score is my score. So we will check for the first two, and this one is just assumed through your data collection. What ANOVA is doing is it's testing the variance between and within groups. So we have this idea of variance and how spread out everything is. ANOVA is giving us two different variances. It checks within group and between groups. So within groups is saying that for group A, not everybody is the same. So how varied is group A? And we can think about all of this due to differences or prerequisites or error or whatever it is. Not everybody in group A is the same. Not everybody in group B is the same. That's the within group. The between group is now comparing the variance in group A to the variance in group B, and then comparing those to the variance in group C. And we want to see, is the variance due to the within or the between group? So we will have two variances, between and within. For example, if I'm looking at hand-eye coordination after ingesting certain levels of caffeine, so high, medium, low, and no, I have four groups. and I'm measuring how many errors they make by group. So these four numbers are different. We can all agree on that, but we are seeing, are they significantly different groups? Is there an effect of how much caffeine you drink on your hand-eye coordination? And P.S., we can also factor this by male and female. So we can add male and female on top of that. We would now have 8 groups. So female high caffeine, male high caffeine, and continue all of that. ANOVA is amazing, you can do so much. Here's your basic formula. That looks easy. Go ahead and click on the Khan Academy website and spend 7 minutes looking at conceptually how is the sum of squares total calculated. And then what ANOVA does is it breaks that down and it looks at how much of the total variance is due to between groups versus within groups. We of course have degrees freedom, and that degrees freedom total is because of degrees freedom between and degrees freedom within. Mean square. This is just the sum of squares divided by degrees freedom. So we can have a mean squared of between, this one divided by this. We can have a mean square of within, this one divided by this one. In fact, that's how we get our F test. It's the mean square between divided by the mean square within. Same thing, here's just what it looks like in Excel or in SPSS. You'll see the same table. So this is my total variance. This is how much variance is between groups, how much variance is within groups. My degrees freedom between and within. The mean square is going to be this number divided by 2. Over here, it's this number divided by 210. My F test is the mean square between divided by the mean square within. Just FYI, that F value is massive for this example. So we use the F distribution for ANOVA. We change that to a p-value. So this p-value has 184 zeros before that 1.4. So this is a significant finding, meaning that number is less than 0.05. So we are 95% confident that there is a significant ANOVA. When we reject the null hypothesis, when we say we have a significant difference between groups, we can only say at least one of the groups is different than everyone else. In order to tell which specific subgroups, we have to do another test called PostHawks. So what this means is that if we have group A, B, and C, and we get a significant value for ANOVA, that doesn't mean that A, B, and C are all different from each other. That could be that A is different than B and C, but B and C are the same. So we can't tell that based on the first result. That's going to be another test. One-way ANOVA has one independent factor, one independent variable that we call factors, and it focuses on one dependent variable, which is going to be our continuous value. Keep in mind that this is not a pre-post. These are different people. So male and female, this is not a pre-post. If you want to do pre-post, that's going to get into Factorial ANOVA. So here we have two factors by one dependent variable. So our factors here could be gender and ethnicity. And each factor has different levels, different groups within that big idea. So if we were doing a two-way ANOVA, also called Factorial ANOVA, gender would have 2 subgroups, which would actually be called sex, not gender. Ethnicity would have 5 groups, meaning we would have 10 different groups. We would have white females, we would have white males, we would have Hispanic females, we would have Hispanic males, and keep going all the way through until we have 10 different groups. And we see, does what group you are in have an effect on whatever dependent variable we are choosing? So I want you to pause this video for a minute and really go through these and see if you can answer them. If you feel good, then go to part 2.